gotta make a one. I gotta make a. Did you give up there? I got most of the pluses. I got like 4 minuses. Like little stuff like on the option, like when you cut up, I kind of slow down so that you keep over here. If you're gonna do a cut block, do a cut block. I kind of got confused what I was gonna do in one of them. I made the blocks and one of them was minus. We got to do better with that. That was not good. After the game, it's like, yeah, I want to get more, but I utilize what we do. They do it in practice. Because if you're going to call and make it call, not just call someone from the or have this coach mind regulate the whole thing. Because he could be walking back and forth with the back up. That's all you do. Well, and you know, like in the red. Oh, yeah. They ain't that much though. Oh man, I was so close. That's the best I ever played. I ain't never supposed to do it like that in my life. Yeah, I was like that. Like, you can shoot it straight. I think the only game I was on was like 1/3 they hit when I was top like 1-0. It's on the whole game.
All right, we ready? All right, so now we're going to move into material that most likely you have never seen. Oh, question first. Oh, yeah. Yep, so it's going to be material that you haven't seen, most likely. We're going to talk about quantum mechanics, we're going to talk about electron configurations, talk about quantum numbers, and so it'll kind of make a bigger picture when we put it all together. So we're going to start with some intro material to the quantum mechanical model. So the first thing we want to talk about is what do we mean by small? Right, we use small to define size. Right, you can say that your car is smaller than the building that we're in. You are smaller than your car, right? But the tires shouldn't be bigger than the car, right? It's a relative size thing. You're comparing two things to see which one is bigger. But there's a limit to how we can use this kind of relative size phrase when we're talking about science. So we can talk in general terms. Bless you. That protons and neutrons and electrons are all small, right? Right, because they're all smaller than the molecule they're a part of, and molecules are smaller than you, and so it's a ratio size kind of thing. But in fact, they are so small that it's really hard to think about. So if you think of a piece of dryer lint, right? Everybody mostly did laundry this weekend. Think about some of the lint you pulled off your clothes. A piece of lint has more electrons than have ever been people on the face of the planet. This little bit of lint has more electrons than have ever had people on the face of. I mean, it's mind-blowingly small, and it's hard to imagine how small those electrons are. Right, really, really small, super small. But the electrons control all the chemical and physical properties of an atom. Right, because you can't change the number of protons, because that changes the element that it is. You can change the number of neutrons, but that changes its mass. It doesn't really change its ability to do chemistry. So the electrons are the driving force behind all the chemical, physical abilities of a given atom. Well, electrons are so small. They are really hard to study. So imagine the last volleyball game you witnessed or a part of, right? You're imagining the volleyball like it's on one side of the net, then you watch it could be tennis, goes to the other side of the net, then you can watch it come back, right? As a viewer of the volleyball, beach ball, you weren't affecting the outcome of the ball's motion, right? You watching it, unless you're a really obnoxious fan, should not affect the back and forth ability of the ball, right? Not true for electrons. An electron is moved in space by light. Right, so when you think about, right, thinking back to your elementary physics, right, so if you are seeing something, it's because the light in the room is hitting the object and bouncing back into your eyes. You're actually seeing a reflection of that object. So you viewing the tennis ball means that the sun has hit the tennis ball, reflected back into your eye, and you're seeing the tennis ball that way. If an electron is being moved by light, it means that if we use light to shine on an electron, that light has actually moved it. So by you trying to see the electron, it's actually moving the electron away from where you thought it was. It's pretty amazing. So the act of observing the electron causes it to do something. Or to react. And so it could react by moving, it could react by recombining with somebody else, it could react by leaving the atom it came from. But it's going to do something. You can't actually watch an electron not do anything. If you're watching it, you're forcing it to act. I mean, think about it. Craziness. So we're going to talk about how do we know what's going on with the electrons and how do we observe things on this super, super, super small scale. Well, we can't use the regular rules of physics. We can't use large-scale physics. We have to come up with this new area of physics called quantum mechanics and talk about what is light, how does light affect electrons, and how do we know what electrons are doing. Are you guys still cold? You're so mind blown by it, you're hugging each other. Just with like, I can't believe it's so amazing. Yeah, could be. All right, so let's talk about what light is. All right, so light is considered electromagnetic radiation. It's a type of energy that has both an electric field component and a magnetic field component. Let's see if I can get that to zoom in a little bit. There we go. So certain properties of light are best described by thinking about it as a wave with this two different types of field, the electric and magnetic field, while other properties of light make it act more like a particle, which we'll talk about here in a minute. So let's talk about the light nature or the wave nature of light first. So here I have my picture. My electric field component is going this way. And the electric field is a region of space where electrically charged particles experience a force. So those could be things like ions, right? They have some sort of charge associated with them, and the electric field is the area that they feel pushed in some kind of way. Then we have our magnetic field component. What kind of particles do you think experience a force in the magnetic field? Magnetically charged particles. All right, so here we have my electric field going up and down, my magnetic field going in and out of the paper. This wave of oscillating fields that are 90 degrees to each other forces light to move forward. So these waves, these oscillating 90-degree opposite waves, bless you. Too many C's in vacuum. There we go. These waves in a vacuum travel at 3 times 10 to the 8th meters per second. Anybody know what we normally call that?
Speed of light.
Right, that's the speed of light, right? Seems obvious. So you have these different waves working together, forcing the light particles to move forward, and it travels at the speed of light. So, for a comparison, I'll put this up here. Sound travels at 340 meters per second, which is why often, right, you'll see something before you hear it. Like if you're looking at an airplane, you can usually see the airplane farther ahead than where you're hearing the sound. So if you hear the sound coming this way, you need to look over that way for the airplane because it's already past you. Lightning and thunder, like this past weekend, you saw a lot of lightning probably before you saw the thunder or heard the thunder. Different speeds, way, way faster. So I now have these two oscillating waves, which means we need to take a second and talk about waves and how we characterize waves. So we talk about waves in terms of a few different characteristics. Most of the time, we talk about it in terms of amplitude and wavelength. So amplitude in my picture here, all right, that one's the amplitude. That is the vertical height of a wave. And amplitude determines the intensity of the light. or how bright it appears. All right, so you can imagine a dim light versus a bright light. That's the amplitude difference. Wavelength is this one. And wavelength is the distance between two peaks of a wave. And this is just about always measured in nanometers. At least for light. Light will be measured for sure in nanometers. All right, so here, again, this is a picture from your textbook. If you have different wavelengths tell you different colors. So you can't tell my black and white whatnot. But it should be, let's see, what colors were they? I think these were like purple, yellow, and red, something like that. But moving down the rainbow. Or if I have different amplitudes, different brightnesses. This one has a very small amplitude, so very dim. This one has a very high amplitude, so that would be much brighter. And you can vary them independently. You could have, right, in this particular case, all the amplitudes are identical, but I could have different amplitudes and different wavelengths, or I could have just different wavelengths, same amplitude, or same amplitude, different. You can vary them without affecting each other. If you want to see it in color, it's figure 7.2 in your textbook. Okay, we can also characterize them by a few other measurements. Frequency is another way to characterize a wave. So frequency is the number of cycles that pass a stationary point in a given amount of time. Right, we use frequency all the time when we're talking about how often something happens. Right, you're standing at a stop sign and you could count the number of cars that pass you. That would be a frequency. You could talk about standing someplace else, watching something else go by. Waves, right, on the beach. You could count how many waves hit your feet as long as you don't go moving around. So since it's a given amount of time, I'm saying number cycles per time. So frequency has units of inverse seconds. So 1/seconds, or sometimes it's written like this. Seconds to the negative first, meaning 1/. Turns out these are related. Frequency and wavelength can be related. Frequency, which is how often something happens, is inversely related to the wavelength, which is the distance between two waves. Right? So if I'm standing here and I see a wave pass every 5 minutes, that tells me something about how far apart they are in physical distance. If the waves all of a sudden start coming by every 2 minutes, it tells me that the distance between them must have shrunk so that they come by more often. And that is related through this equation. So frequency is inversely proportional to wavelength. So here I have frequency. Here I have wavelength. And c is our speed of light. Which is 3 times 10 to the 8 meters per second. Eventually I'll figure out what temperature to put the room on. Right, so I have meters per second. Wavelength is in a distance, so in meters of some sort, which means the frequency is going to be left in inverse seconds. So we can put this all together in some context, which you've probably seen before, one of these color lines, which on grayscale looks ridiculous. But imagine this in color, right? So the electromagnetic spectrum is made up, we don't have a color printer right now, so sorry, it's going to be all black and white. Unless someone wants to make a generous donation to the chemistry department, buy me a color printer. No, okay. Thought I'd ask. All right, so here I have frequency. Right, going from 10 to the 4th to 10 to the 24th. So going from low frequency to high frequency. If I'm at low frequency, I'm at low energy, but I'm at high wavelengths. Right, so my wavelength is going from 10 to the 5th down to 10 to the negative 15th. So they are inversely related. If you're at low frequency, you're at low energy, but high wavelength. Over here, high frequency, high energy, low wavelength. So here I have we have radio waves, which you can imagine are like big, gigantic, slow-moving waves. Low frequency, high wavelengths, because they have a big distance between them. Then you move over here, passing through AM TV with rabbit ears, that kind of TV, FM, cell phones, into the microwave, which is slightly higher frequency, slightly lower wavelength. Then we move from microwave into infrared light to visible light, which goes from red, which is the low frequency, high wavelength. That's not right. That should be this. Typo in the book. That should be this guy. Where violet has a high frequency, low wavelength. And then eventually we pass through ultraviolet X-rays and gamma rays, which have very high frequency and very low wavelengths. Small wavelengths. All right, that's probably most of the review so far, right? Okay. So let's talk about some physics. Baby physics, just a little bit, just a little taste, a little teaser of physics. That way when you get to physics, you'll be ready, unless you've already had physics, in case you're an expert at this. All right, so we have waves. And waves have the ability to interact with each other in two different methods. And it's going to be called interference and diffraction. Sorry, my sentence got cut off. Okay, so waves can interact with each other in characteristic ways called interference and diffraction. So let's talk about interference first. Interference is kind of what we imagine, like when you think of the word interference, especially in terms of football, like over this past weekend, right? If an interference call is on the field, it means that one of the players prevented the other player from completing his play as he should have. So interference could be that, could be preventing something from happening. And that is destructive interference. which is this one over here. So I have two waves out of phase with each other. So I have, the waves are at the opposite ends, and then they crash into each other. Then they go the wrong way, and then they crash into each other. That causes them to cancel out. So destructive interference is the canceling out of waves. But we can also talk about constructive interference. Under constructive interference, it means that I have two waves that are now in phase. They're going the same way. Both of them are hitting the high points, and both hit the low points, and back up to the high, then back down to the low. They'll actually add together and make a wave that was twice as tall as either one of them. All right, so now they add together. So constructive interference is building up of waves. This is my next slide. Yeah. All right, so that's interference. We can talk about them adding together or canceling each other out, depending on how much in phase they are with each other. Then we also need to consider diffraction. This is when a wave, so now we're looking top down. So the waves are actually coming in and out of the paper, right? Up and down and up and down. So we're looking at them top side, so they look flat, but really they're going in and out of the paper. So I have this wave going up and down, and it hits something with an opening. It's going to force the wave to bend in order to get through it. And that's called diffraction. Diffraction is the bending of light when passing through an opening. So this is what happens with light. Light works like this, ends up making these waves. You want to call it like this? So my light has been bent when passing through the opening, and now it makes these curved waves. If light was a particle, it would look like this, right? They would hit the barrier and just stop, or shoot right through, which means since we see this, light is definitely wave characteristics. It's also possible to have light pass through two openings. We'll go crazy. So if I have my light looking like that, we'll end up with two waves that can interact with each other. And we'll see, actually, if I held up a piece of paper over here, we would see kind of a pattern. So we send in straight light, but we get out this constructive/destructive interference pattern. It's pretty neat. Pretty neat. I know you guys do that as a physics experiment, so I'll wait for you guys to get to that point. It's pretty exciting. All right, so waves. Light definitely acts like a wave. Let's talk about how light acts like a particle now. All right, so early 1900s, they had pretty much proven that light behaves like a wave, right? They were able to do these experiments send light through a slit. It makes these waves. They were able to add light together. They're able to have light cancel itself out. Good. But then the photoelectric effect was discovered. So the photoelectric effect was the observation that metal can emit an electron when light shines on it. Weird. Right? So it's just acting like a wave, it would just bounce off the metal. But it turns out that if I shine light on certain metals, it actually forces an electron to pop off and do some chemistry. This was mind-blowing. It still is kind of mind-blowing, right? The idea that light can force chemistry to happen. Super awesome. We use it all the time, you just don't think about it. So, the scientists at the time so it was shown that different frequencies of light produced electrons. So I could vary the frequency and produce a few different amounts of electrons, but there was a lower limit. There was a low frequency that I couldn't get electrons to pop off. So, a kind of famous physicist named Einstein, you may have heard of him, came up with an explanation for this experiment. He said that light energy must come in packets. Right, that there is clumps of light energy that when it hits the metal, this clump, this packet of light energy forces an electron to come off. It's not acting like a wave would just bounce off like we just saw in the diffraction, right? It would just move away from it. But there must be some sort of like amount of light that kind of shows up together with enough force to cause something to happen. And so he described this mathematically using this equation, E equals h nu. Okay, so E is going to be energy, measured in joules, which is a measurement of energy, which makes sense. H is Planck constant. Which is 6.626 times 10 to the negative 34th joule seconds. That little dot means multiply by joule seconds. Which is a weird idea, but right. So Einstein knew joules, and he knew that was related to frequency, right? Different frequencies produce different. So you have to have something in between that has the right units that makes the math work out. So he developed a constant that worked every time. And it has to have units of joule seconds because we have frequency and energy. All right, so then we have our frequency. In inverse seconds. All right, so packet of light is kind of a mouthful phrase. So they changed packet of light and called it a photon. It's a known amount of light, a photon. So now we have two equations. I just lost the other equation. There we go. Right, E equals H nu. And we had one a few minutes ago that also had frequency in it. So we have these two equations. All right, and they both share a variable. So I have frequency is equal to speed over wavelength, and I have energy is related to this constant times frequency, which means I can make a third equation that combines that information. If I put a box around, it means for sure you need to know it. It's kind of like my hint. That box it, super important. So those are going to be three equations we have to know for this chapter. So let's go ahead and put one into practice. So if you have your calculator out, awesome. If you don't, go ahead and find it. We'll do one practice problem, and then I'll make sure we have time for the quiz. All right. Let's see where my slide is. All right, so I'm assuming people still own DVD players. All right, that's not quite that old technology. This question used to be about a CD Walkman. I realize no one carries those anymore, so I had to change the question. So a DVD player still uses a laser, right? If you ever looked inside there, there's like a little red light in there. That's a laser light. And it emits light at 685 nanometers. Let's talk about what amount of energy 1 mole of photons of this laser light contains. So, right, I've given you, if it's in nanometers, is that speed of light, wavelength, or frequency? There's the wavelength. So I gave you this. And I want to know energy. So which of our three equations should we use? 1, 2, or 3? 1, 2, or 3? 3, right? 3, because that relates energy to wavelength. And the top two things are constants. All right, so let's go ahead and start plugging what we know into that equation. E equals hc over wavelength. All right, so we're looking for E. And h was a constant. And c is a constant. All right, what should my units of energy be at the end when I'm all done with this? What do I measure energy in? Joules. Okay, let's see how my units are looking right now. Can I cancel out any units on the numerator? Is there anything I can cancel out? Seconds, right? Because I have seconds and inverse seconds. I'm close to being the right thing. What is the issue between this unit and that unit? Right, they don't cancel. So how do I get nanometers into meters? How many nanometers per meter? 9, yeah. So I want it to be in meters. So now my nanometers cancel out, and my meters cancel out. So that's going to be the trick to these questions. They're often going to give you wavelength in some sort of crazy unit. You just need to know you need to convert it into meters, otherwise it doesn't cancel out. All right, so let's plug it in and see how this turns out. Let's see. And then we'll do the second step. This is step 1. All right, 6.626. Negative 34 times 3, 8, divided by. There is something ballpark like that. Seems about right. Okay, good. So then, this is joules of 1 photon. Just one photon. I want to know about whole mole photons. So, what number do I multiply by to get to an entire mole of photons? Yep, our Avogadro's number. This should be a pretty big number, I think. 2.90. 19 times 6.022. Third. Let's see. How many significant figures do I get? 3. I get 3. So 1.75 times 10 to the 1, 2, 5. Good, good. All right, we will stop there so you guys have time for your quiz. We will finish just about the rest of Chapter 7 Wednesday, and then we'll do the end of 7, start 8 on Friday. Moving right along. All right, you will need a calculator for the quiz, so don't throw it away. And make sure you leave your name. Visualize everybody that's going to be mine. Thank you.